What?
We are not going to say like she was.
Yeah.
So, I don't know, maybe we should get started. Yeah, so last time we started learning about vector spaces, right? Vector spaces and some axioms about vector space. So basically, these axioms will guarantee that the concept of linear combination of objects makes sense in a very nice way, very similar to geometrical vectors in Rn. And then we learned the concept of subspace. So, and one main reason here we're interested in subspaces is a lot of times problems that we are dealing with and vector spaces that we need in different sort of settings, these appear to be already subspaces of some well-known vector spaces, some big vector spaces. So the concept of subspace is very practical, in application. So a set of vectors inside a big vector space satisfying some properties. Well, for us, it means essentially a subset, right, of a vector space that itself, under the inherited operations of addition and scalar multiplication, it forms a vector space. And we learn that essentially we need to check the so-called closure axioms. If we, that's also one of the practical advantages of working with subspaces, is that you already know you've already established a big vector space, already checked all those axioms for that bigger vector space, and all you need to do is to check the closure axiom. So you check that the zero vector is in that subset to just show that it's non-empty. Typically that's how we prove that it's non-empty. And then the closure axioms means it's closed under addition and scalar multiplication. And we studied some examples and some non-examples of subspaces. I think the last one was this example of 2x2 matrices, the set of 2x2 matrices whose determinant is 0, the singular matrices. These in fact, 0 is there, the 0 matrix is there. It's closed under scalar multiplication also, but it is not closed under addition. So I picked these two examples, these two vectors now, for us of singular matrices, right? Their determinant is 0, but when you add them, you get the identity matrix, which falls out of the set W of singular matrices because it's invertible. So are there any questions before we proceed to some more topics? I want to now start on learning about span In particular, do you have any questions about the homework problems or anything of that nature? Okay. So there is a very important construction as far as subspaces are concerned. Essentially, we can think about it this way. There is essentially one way of forming a subspace, you know. All you need is a set of elements in your big vector space, and you just consider all possible linear combination of it, like all possible way that they can expand, you know, in a linear way. And this turns out to be a very important construction, and this is, you know, theoretically the only way you can make a subspace, but there are equivalent ways to this. But you know, all you need is a set of vectors inside a vector space and linearly expand them, which we call them a span. So here's the definition of a span. So here S is a subset of a vector space V, okay? So I'm not assuming that S is already a subspace, because that defeats the purpose of making a subspace, right, already. So you just have a set of elements, right? Elements of a vector space, as you know, we call them vectors, right? So you have a set of vectors. This set does not have to be even non-empty, it could be empty. So I will write a definition for the case of empty, which is the trivial case, but it doesn't have to be finite. So it could be infinitely many vectors, okay? So the span of S, or sometimes linear span of S, but because we're working in linear algebra, I just dropped the word linear, is the set, so span of S, right? So that's the notation, is defined to be, as I just said in words, all possible linear combinations. So how do we write that? Instead of all possible linear combination A1 V1 plus all the way to AN VN, where A1 through AN are scalars, V1 through Vn are vectors in S, and of course N can be any natural number. I mean, you're not fixing the number of vectors. So any number of vectors in S are going to be considered an all possible linear combination. So I would say N is anything in natural numbers, okay? So we were just talking about the span of a set as a major construction of subspaces, okay? So we consider, so a set is given to us like S, the set is just a set of vectors. We consider the set of all possible linear combinations of the vectors you can imagine from that set S, okay? And this is called the span of S, and also the case of the empty, if you just consider no vectors and what is the span of S? I just define it to be the trivial subspace, I mean the trivial set 0. So span is obviously a subset of V, but in fact, we will show that this is going to define a subspace, a vector subspace of V, and any subspace is obtained this way, basically. Okay, so this is a very important construction. So note some remarks here. I want to say that it's clear that the span of S is a subset of V, according to our definition, because if you linearly combine some elements in S, which are in V already, then they should belong to V then, right? I mean, the linear combination will belong to V. That was the very first motivation for defining a vector space, right? So span of S is a subset of V. We will show that it's indeed a subspace of V as well. And also notice that S itself is inside its span. Isn't it the case? I mean, so if you give me any vector V in S, all I need to do is multiply it by 1 times V, right? It's a linear combination of that element. As I said, this N could be any natural number, right? So any natural number. So we can pick just one of the vectors in S, right? And just multiply it by any scalar you want, right? So this defines a geometrically in Rn. If we were in Rn, this would define a line through the origin. If I multiply by 1, it's a linear combination, isn't it? So then this means that obviously S is a subset of its own span. So now what I want to show also is in fact a few more properties. If T is a subset of span of S, then so if you consider a subset of the span of S, then its span of T is a subset of span of S. And think about it. I mean, the proof, let me write it as a proof. I mean, obviously, if T is a subset of span of S, what are the elements of T? The elements of T are linear combinations of elements of S. And a linear combination of linear combinations is again linear combination, right? So that's it, that's the proof. So a linear combination of linear combinations is also a linear combination, essentially. I mean, I put it in quote unquote, if you want, is also a linear combination, right? So that's all it says. Okay, right? Is it clear? Any question about that? So some corollary here is that, in particular, this construction of span has this property that if T is a subset of span of S, then span of T union with S is a span of S. So what are we saying here? We're saying that if T is already, you know, a set of some linear combinations of vectors in S, if you combine these vectors with the vectors in S linearly, you are still in span of S and vice versa. So why do we have that? I mean, again, the proof is easy. It just follows from the definition that from the previous proposition, it's clear that span of the union S and T, right? So this is you know, this notation is union, right? So the span of S union T contains span of S. Why do we have that? Because of the previous proposition, right? So so this is inclusion, right? So it contains span of S. Why do we have that? Because S is basically inside the union of S and T, right? So when you span all vectors in S, you're in particular part of the span of S union with anything else. So because you can take the coefficients of anything coming from T to be equal to 0, right? So that's what we have. And conversely, we have also span of S union T is a subset of span of S in the other direction, right? And this is because S union T is a subset of a span of S. Why do we have this? Why do we have this thing here? Well, S is a subset of a span of S. That was this remark right there. T is a subset of a span of S also because of the assumption. Right? T is a subset of a span of S. So both S and T are subsets of a span of S. So clearly a span of these vectors is a subset of S, span of S. So one more property here. Proposition. And this is a very important proposition that if S is subset of V, then span of S is a subspace. Not only a subset, but it's a subspace of V. Okay, so if S is empty, then span of S is the 0 vector, and that's a subspace of V, right? But sometimes we call it the trivial subspace, right, of V. Suppose S is not empty, okay? How do we show that span of S is a subset of subspace of V? We know it's a subset, so how do we show that a subset of a vector space is a subspace? What do we need to show? We show span of S is a subspace by showing the closure axioms, right? So the closure, you know, properties or axioms. So what do I mean by that? If U1 and U2 are in span of S, is it correct that U1 plus U2 is in span of S too? So being in span of S means what? Means nothing but a linear combination of vectors in S. Right? So that's the meaning of being in span of S. So U1 is a linear combination of vectors in S, right? So some linear combination of some vectors in S, right? So is U2. Now, if you add them, aren't we getting a linear combination of elements in S, right? So it's just probably with more elements involved, but it's still a linear combination, right? So you see the definition is very natural, right? I mean, linear combination, since we didn't put a certain number of elements, you know, in the definition, like, I mean, any linear combination, as long as it's finite, it's okay, right? So this implies that U1 plus U2 is another linear combination of elements. Which is exactly the meaning of being in span, right? I think it's also clear that if U is in span and alpha is a real number, right? Then you rescale this, is it still a linear combination, right? So, I mean, if U is A1 V1 plus, right? Plus some AN VN, right? For some AJs in R, VJs in S, right? So meaning of, so if I multiply by alpha, do I get a linear combination of vectors in S again? Alpha U is alpha A1, right? Times V1. So you see, I'm using the axioms of vector space. Alpha times the sum is the sum of alpha times each one, distribution. And then this is exactly where I get to combine alpha with each AJ as a scalar. And we had all those axioms for vector space. So I can write it this way. So this gives us a linear combination of elements in S, right? So span of a set, a subset of a vector space, is really a construction for subspace construction, right? Subspace generating construction is by span. Taking the span of any vector, any set of vectors. So let's take a look at this example. The solution set of the equation x plus 2y equals 0, where just one linear equation, is a subset, is a subspace of R2 okay, y. So I mean, more generally, I want to, we will see that solution sets of linear homogeneous systems of equations should be a subspace. Okay, so this is a baby example of linear homogeneous. What makes it homogeneous? Equals to 0. And so the solution set is a subspace of R2. So what is the solution set? So remember that x should be equal to minus 2y, right? So x is the free variable, for instance, y is the free variable, x is solved in terms of y. So y, if y is s, then x is minus 2s, right? So the solution set S is the set of pairs minus 2s comma s, right? Such that s is any real number, right? Now, remember that whenever we solve linear systems, we try to pull the parameters out and write them as sums. Now, it's time to think about it in the context of linear span. There is no leftover, though, in this case, right? I mean, there is no initial motion from the origin to that subset or solution set, exactly because the equation is already homogeneous. It's already, the solution set already contains this zero vector. Okay, it's exactly because the equation is homogeneous. So there is no initial motion from the origin to that set. We are already there. So with one just pulling out, I get the set of S times -2 comma 1s, where S is in R, right? So, and the point of this example in the context of span is by this move, like pulling the S out, I'm just getting all possible scalar multiplication, scalar multiples of one vector. So I can write it as exactly span of this single vector. Because what's the meaning of span of one vector? So span of one vector means all possible scalars multiple, because you have only one vector. So how can you linearly span it? You just multiply it by one scalar arbitrarily. If you have more than one vector, then any linear combination of the two would have been the linear span, right? So this is a span. Once it's a span, it's a subspace. Maybe I should have called this, we traditionally call that S, right? But it's okay. So S is linear subspace. Never wrote linear because we're studying linear algebra. So if I had x plus 2y equals 1 though, would it be a linear subspace of R2? Well, the solution would have been y is s and x equals -1 minus 2s, right? See, this is what I'm saying. So the solutions are -1 minus 2s and s. I have to pull out the translation vector first, right? You see this.
It's equals to 1 minus 2a. So you are taking by questions. Minus symbol for 1.
Correct.
One
It's 1 minus. So 1 minus 2s. So plus s times -2, right? Okay, now this is not a subspace. I mean, the set of all. Why? Because this is not exactly, are we taking all possible linear combination of these vectors? No. You see, this initial motion just is with 1. 1 times that. You don't take 2 times that plus this or any other real number times that. So the set S here is the set of all 1, 0 plus S times -2, 1. Is not a subspace here. So how do we show that a subset of a vector space is not a subspace? There is an algorithm, simple algorithm, step by step, right? First check, is 0 there, right? The 0 vector. Then is it closed under, can you find 2 vectors that when you add, it falls out, right? Or can you find a scalar and a vector in there, when you multiply, it falls out, right? To just sort of come up with counter examples of the closure or emptiness, right? So, well, in this case, it's clear that the 0 vector is not there, right? I mean, is the 0 vector there? I mean, if 0 was one of these elements, then 0 plus 2, 0 would have been equal to 1. So, I mean, 0 is not in S. So clearly this is not a subspace. So very quickly, we're able to show that it's not a subspace by just showing that 0 is not there. So any questions so far? So the construction of the span construction is extremely important in linear algebra. So this is the following definition is perhaps the first step towards the very fundamental concept of basis in a vector space, which means I'm looking for a set of vectors that plays the role of building blocks for my vector space, like Lego. You want to make a Lego as your vector space. How many different pieces you have to make, you know, this big building and so on. And oftentimes you just have finitely many, you know. So those vector spaces which can be built, can be constructed by finitely many vectors, let's say, and all possible linear combinations are called finite dimensional vector spaces. Okay, so towards the concept of basis, towards the concept of dimension. So this is like a very important point now. So from this, a spanning set of a vector space is a subset S such that its span is the entire vector space, right? I mean, consider all possible linear combinations. So the first question that I ask is, if I give you a vector space, any vector space with those axioms, right? Is there a spanning set, right? Well, if you think about it for a second, that's an important question, but that's not difficult to answer at all, because if I take the entire set of vector space as your subset, then its span is the space. But this is, you agree that this is not the most economical way of constructing that vector space. You're just saying, give me all of the vectors I constructed for you. So there is no advantage of doing this. So once you think about finding a minimal set of vectors that can span your entire vector space, you're exactly thinking about the concept of basis. Because I just defined the basis that way. The minimal set of vectors whose span is the entire set, entire vector space. It's called the basis, okay? But we'll get there, okay? So I'm just giving you the motivation why we're doing this, okay? So span of, so the spanning set, so this is for us now just a definition, first building block towards dimension and basis. So a spanning set is just a subset whose span is the entire vector space, okay? So, and I just told you that obviously V is a spanning set for V. So V is a spanning set for V. But that's not a big deal at all. So some better examples than this trivial. So let's fix R2, okay, to just practice, you know, this with geometrical two-dimensional vectors in plane, okay? And think about the following examples, which ones could be a spanning set, which ones are not. So maybe the most obvious example in some sense is the set S with the canonical basis vectors, right? So which is ultimately what we want to call the canonical basis of R2, which is 1, 0, 0, 1. Why is this a spanning set? All we need to do is show that any vector xy arbitrary, right? We can write it as a linear combination of these, which everybody knows how to do it, right? I mean, xy is how many times 1, 0 plus how many times 0, 1? if you can show a linear combination can be generated, then you're showing that R2 is spanned or generated by this set S, right? So what are the obvious coefficients here? X, Y. Right. XY is an arbitrary vector in R2. I want to show that it's generated by 1, 0, 0, 1. And yeah, it's really X times. Exactly. We want to show that. So this example shows that S is a spanning set. Because all possible linear combination of that generates the entire vector space. And this is the calculation. It shows that anything in R2, right, is generated like that. That's a linear combination of these two vectors. So let's now think about some other examples. What about these two vectors? Do you think this is a spanning set? Again, think about, obviously the span of S is a subspace of R2. This is what they have proved already. But is it the entire R2 or not? So again, once again, how do I write XY? Any arbitrary vector in R2. Can you write it as a linear combination of these two? So what times 0, 1 plus what times 1/2 0 would give you XY. And if you think about such a problem, it's just nothing but solving linear equations, right? I mean, you can put alpha and beta and try to see if this has a solution or not. But since 0, 1 and 1/2 0 have coordinates only in the X direction and Y direction, so it's easy to solve that system. So if I want to put alpha and beta, what will be alpha and beta, do you think? Actually, there's a unique solution. So there's a unique way of writing that. So you can convert it to a system and solve it, but since it's, as I said, these are separated, you know, in the X and Y direction, it's easy to find the alpha and beta. So if I multiply by alpha, the first one will be 0 alpha, the second one will be beta half and 0, right? Which gives us beta half comma alpha, and this should be XY. So then what is alpha? What is beta then? We're trying to find alpha and beta.
No, sequence X and Y.
Mhm.
Now alpha X should be at alpha side and beta on Y side, or we can use beta by 2 and alpha will be YX or XY.
If you switch 0 and 1 and 1/2 and 0, yeah, you're switching alpha and beta at the same time. So I define alpha to be the coefficient of 0, 1, and beta to be 1/2, coefficient of 1/2 and 0. So there's a unique solution then that way. So from here, alpha should be Y, right? And beta should be 2X. So yes, indeed, XY, any XY is a linear combination of those two vectors, right? So I mean, if 5, -3 is an arbitrary vector, right? How can you write it as a linear combination of 0, 1 and 1/2 0? So it's -3 times 0, 1, right? Plus 10 times 1/2 0, right? So this is our construction now. Okay. So this means that S is a spanning set. Right? You still have some questions?
Let's have a look at example number 2, if you see, the XY sequence is you started with alpha into 0, 1, and we come to have 1 by 2 into 0.
Mhm.
So why do we change the sequence from 0 alpha plus beta by 2 to 0? The sequence is XY now, and third step we just made it beta by half and alpha. So will it be considering as Y and X or X1 as a
So probably you're comparing it to this, right? To the
Yeah.
first example, yeah. So the first example could have been the same, right? I mean, XY. Can we find some alpha times 1, 0 plus beta times 0, 1, right? But this gives us alpha beta then, right? So this tells us alpha should be X, which is what I did, right? And beta equals Y.
Okay, with 0, 1, 1, 0, that formula. That's the same.
Yeah, 0, 1. So the order doesn't matter, right? I mean, so I'm just saying this set of two vectors, 0, 1 and 1/2 0, they form a spanning set. So all I need to show is any vector in R2 is a linear combination of these two, which is what I did. I showed that an arbitrary vector is a linear combination of these two by finding these coefficients exactly. And here is an example how we can do that. And we can switch things around, but then 10, I have to switch the entire thing around, like this and this can be switched, but alpha and beta cannot be switched. So so thinking about that, do you think this is a spanning set? 1, 2, 0, -1. Do you think this is a spanning set for R2? Once again, I put XY. Can I write it as alpha times 1, 2 plus beta times 0, -1, right? This gives me alpha, comma, I guess 2 alpha, right? 2 alpha minus beta. And this is supposed to give us X and Y. So alpha should be X then, right? Yeah, alpha is X, and what is beta? Beta should be 2x minus y. So every vector you give me, I can write it as x times 1, 2, right? Plus 2x minus y times 0, -1. So yeah, I can write any vector, arbitrary vector, as a linear combination of those two vectors. So this means again that S is a spanning set.
So in this example, if I change to 1, 2, and the 1 minus 2. So how do you
1 minus 1?
Yeah.
Mhm.
then beta minus 0.
Let's check. So 4, 1, 2, and 1, -1.
Yeah.
Okay, so then I would be trying to solve this system of equation. Long time ago, I told you that many problems in linear algebra boils down to solving system of equations. I define a concept, and naturally, it's about solving the system of equations. And here's the system. So alpha plus beta, right? 2 alpha minus beta. So you're solving alpha plus beta equals x, and 2 alpha minus beta equals y, which you can solve by elimination, for instance, Gaussian elimination. You can add and get, in this case, you get 3 alpha equals, so alpha is, I guess, 1/3 of x plus y, right? In this case. And then beta will be x minus that. Right? Which means, I guess, 1/3 of 2x minus y.
That's what the third out.
Does this work, right? If you add them now, you get x, right? Yeah, so this is still a spanning set then, right? So hopefully you get the idea that, yeah, there are many spanning sets for a vector space, right? But so far, all of our examples had 2 vectors in them, right? Does it have to be so? No, because the entire R2 is a spanning set for R2 as well. So S is a spanning set. So 5 doesn't have to be to have 2. Can you give me an example of a spanning set with 3 vectors for R2? Yeah, what is the idea? Say that again.
I said like put 0, 0, then it will be trivial solution. Like 0 is also involved. So we have 3 vectors, 0, 1, 1, 0, and 0, 0.
You mean I add a vector to any of the above examples?
Yeah.
Any vector. Yeah, that's right. That's the idea. Because when you put in more vectors into the set, the span is not supposed to shrink. So if 2 of them is already enough, you just add anything you want to that, and still the span should generate R2. What else can it generate, right? So exactly. And why not just the canonical one, right? And just add anything you want, like pi comma e. This is artificial, right? Because now any vector, isn't it x times 1, 0, right? Plus y times 0, 1, and then plus 0 times pi e. So this is just the linear combination I have in mind. So it's a spanning set, right?
And then we are moving from R3 to R2.
We are still in R2.
If there is third entry considered as R3,
If we,
if you have third dimension like pi e, another entry, also not be considered as R3.
yeah, it's an element in R3, but then you can't linearly combine it with 0, 1 in R2, unless you make them. So in this example, V is R2, the big vector space. I didn't change it to R3.
This is the only way that we can do it, right? 0 times.
That's a very good question. No, oh, you mean this is the only way to write x, y, 0?
Yeah.
That's a very good question. Do you think that's the only way?
Yeah, like if you change x with some alpha, beta, then the coefficients may differ, but we will be having the span as well. In this situation, as we are taking 0 into the x. But one also should run a function in third value of x, y, and one of 2. Here, one is 2-dimensional world.
Yes, that's.
0, 0, 1, 5, are only in the 2 tuple. Yeah, but 5 not clear, and it is like you can add this to 5, like x and 1, 0, 5, 0, 1, that is to add this. Because this span, that's it, this is span. But 1, 0 is not, you can add 0 and 5.
Yeah, we can write alpha times 1, 0, right? Plus beta times 0, 1, plus gamma times pi, right?
Yeah.
And the question was, is this the only way? That's a very good question. Because now that we're adding one more, then it's, and this is one selection, alpha equals x, beta equals y, gamma equals 0. Most likely the answer is no, there should be more than. So you see the system that we get is what? So we get alpha plus gamma pi, right? and beta plus gamma E, right? And finally, that's it, right? Yeah. And you want this to be equal to XY. So the system that you're trying to solve is you're getting alpha plus 0 beta plus pi gamma, right, equals X, right? Oh yeah, thanks for. Why did that come out fast? All right. So, and then what is the second equation? 0 alpha plus 1 beta, right? Plus E gamma equals Y, right? So you see here we are having, yeah, it's a sort of an underdetermined system because, and you can try to solve this to see for yourself, you know. So what's the augmented matrix? 1, 0, pi, right? And then 0, 1, E, right? Okay, so this system is already in echelon form, right? It's already in, and it's already in even reduced row echelon form, right? So thinking about making the solutions, right? So what do you think? This is the free column, right? So gamma could be any arbitrary real number, right? So how do you solve this? Alpha equals X minus pi gamma, right? And beta equals Y minus E gamma. And gamma is any real number. So what are the solutions? Alpha, beta, gamma will be X minus pi gamma, Y minus E gamma, and gamma. So if I'm taking gamma as the real parameter here, which I can just pull the gamma out and the rest out, X, gamma, Y, gamma 0, I guess, right? Minus gamma times pi, E, and 1. Right? So alpha, beta, gamma live in where? Live in R3 as a vector. So the solutions that I'm looking for this time should live in R3 because I have 3 vectors to consider, right? 3 vectors, 1, 0, 0, 1, pi, right? So the coefficients alpha, beta, gamma, you want to solve for them. The solutions for that live in R3, right? Not in R2. Is it clear? Whereas in the previous cases, those solutions alpha and beta, comma, alpha, beta, comma, alpha, beta live in R2 already. So this is the entire solution set. Gamma is free, right? Any real number. So which one did I choose naturally? Gamma equals 0. This is what I chose. So then alpha is X, beta is y, and gamma is 0. This is what I chose here. See? You see that? So, but to answer your question, whether this is this time a unique way of finding alpha, beta, gamma, absolutely not. It's just one of them, and all other possible choices for alpha, beta, gamma are parameterized here. So you choose any real number gamma, then other than 0, you get a different combination. For instance, if I pick gamma equals 1, then alpha will be x minus pi, and beta will be y minus e, and gamma will be negative, gamma will be 0 minus, is this correct? Minus one, yeah, because I subtracted, right?
It's spanning R2 and also R2, right?
No. That doesn't make sense. R2 is spanned by, the conclusion here is R2 is spanned by these 3 vectors. But the solutions for alpha, beta, gamma, those live in R3 because we are thinking about 3 vectors to span. So you have to think about it this way. To solve a problem in R2, this problem in R2, we are appealing to a system of equations whose solutions live in R3 because we're thinking about spanning 3 vectors this time. So one more. S is V, the entire vector space. Is that a spanning set? We showed that right already, but if you are still in doubt, any vector can be written as 1 times itself, right? So if this is already in your set, which is the entire space, then so this means that V is a spanning set for V. That's how we can represent any vector then. Now some non-examples. For R2, inside R2. Think about this, a singleton 0, 1. Would that be a spanning set? Well, since these are supposed to be non-examples, you should say no, but why? Why can this not span the entire R2 for us? Correct, right. So let's consider the span of S. Let's realize it. What is it? Isn't it just the set of all S times 0, 1s, right? That means the set of all 0, comma S. Would that be a spanning set? And you should say no by simply bringing a counterexample. Can you give me a vector in R2 which does not belong to the span of this? For example. Okay, so that cannot span the entire set, the entire space. The problem cannot be immediately solved by adding vectors. You may just add vectors, but wrong ones. For example, this set has 3 vectors, but still cannot span the entire R2. So I have 3 vectors. Do they span the entire R2? What do you think? What do you think about the span of S? Any linear combination of these? You see a relationship between X and Y coordinates. The ratio is 2. So they are on the line y equals 2x. In other words, this span of this is the same thing as the span of the entire thing. Remember the proposition I proved. If these already are in span of one of them, then when you add these to the set, then the span wouldn't change, right? So span of S is the same thing as span of the first vector, because 3, 6, and -1, -2, they belong to span of 1, 2 already, right? Because they're just scalar multiples of that. So, but span of 1, 2 is the set of all vectors of the form S times 1, 2, right? Where S is a real number, any real number. And so you're just thinking about S comma 2S type of vectors. Would that give us all possible vectors in R2? No, because give me a counter example. For example, 0, 1, right? Does not belong, right? It's not there because 1 is not 2 times 0. Is it clear, right? Okay. Can the empty set be a spanning set for R2? Well, what is span of S? By definition is 0. For us, it's just the 0, 0. That's the span. It's not the entire R2, right? It's just one vector. Only one vector 0, 0 in it. What's the span? What's the span of the 0 vector in any vector space? Just the 0. And it's not R2. So hopefully these examples, I mean, I purposefully spend some time on these. So you think about how we could possibly find the spanning sets. You know, some ways we discussed, like, okay, it's really about solving system of equations, you know, in R2, you know. So, but these systems may live, the systems may be in R3 because you're thinking about spanning 3 vectors, right? And so on. Any questions so far? So do you agree that any subspace also is a span of something, you know? I told you that this is really, really the only way of constructing a subspace. So span, by finding span of a subset, you're finding a subspace. Yes, but conversely, again, that's true because a subspace of any vector space is the span of itself. So, right? I mean, it might not be the most economical way to do it, but this is the construction, right, for finding subspaces. So you just collect a bunch of vectors and span them, it gives you a subspace. Now I'm towards the concept of dimension and basis again. So what I need to do is for you to define the fundamental concept of linear independence. So a subset S is called linearly independent. Okay, so linear independence is about, in some sense, is about the question you asked, whether there's a unique way of representing things. And this boils down to a very particular case. If you can check that, then that's it. So what is that particular case? The particular case is, okay, so the zero vector, right, is in span of any set, right? Do you agree? So span of a set is a subspace, so obviously it should have zero. But how do you get that zero? It's just you put the coefficients equal to zero, right? Zero times one of the vectors in S, that gives you the zero vector. So the zero vector is always in the span, right, of any set. But the question is this the only, way to generate zero or not? So we say a subset is called a linearly independent if the equation alpha 1 v1 alpha n vn equals 0 has a unique solution has a unique solution. What should that be if the solution is supposed to be unique? It's all zeros, because that is a solution. So the unique, then it means so here all the v1 and vn are selected from S, of course. Maybe instead of the equation, I should say if any equation of this sort, that's a linear combination of some vectors in S, right, produces the zero vector. And the only way that you can do that is by putting alpha is equal to 0. And no other way will do that for you. Okay. So let's think about this in context of some example, right? So yeah, all the alphas should be 0. There's no other combination that you can find that gives you the zero vector. So let's think about S equals 1 0 and 0 1, right, in R2, right, which is your V here, right? So is this set linearly independent? So let's write a linear combination. Write it equal to 0, right? And see if you get alpha equal beta equals 0, the only way. So, but this is clear, right? Because this is giving us alpha beta equals 0. That's the only way. You can't come up with any other linear combination, any other choice of alpha beta, which generates 0 linearly. Right? So this means S is linearly independent. Is this clear? Any question about that? Yeah. So, and this is exactly, now that we have this set of vectors already, we show that it's a spanning set and it's already also linearly independent. I will take this as the definition of a basis. A basis is a subset which is both linearly independent and spanning. Yeah. So in some sense, it's the optimal choice as far as the number of vectors and the linear relationship between them. So, what do you think about this? This is a set of three vectors in R3, in R2, right? So obviously this is still spanning, right? Because I just added a vector 0, 0. Okay, when you add vectors to already a spanning set, you know, they're still spanning, right? But is this set linearly dependent or linearly independent? So is the only way to represent the zero vector as a linear combination of these guys? Is it through 0, 0, 0? Zero, zero is a linear combination of 1, 0, 0, 1. The only way is 0, 0, 0, no other ways? How about this? Not the same. I had 0, 0, 10. It's still 0, 0, but it's not the choice of all three zeros. That's not. So this means that these are linearly, not linearly independent. Whenever it's not linearly independent, we call it linearly dependent.
Which would have the unique.
The unique solution, yeah. In fact, if I add anything else to 1, 0, 0, 1, that would have ruined it, right? You see? One, right? This is also not linearly independent. Why? Can you give me a linear combination of these, not identically equal to 0 everywhere for every scalar that you need, and it leads to 0, gives you 0. Can you give me a linear combination of these that generates the 0 vector in a non-trivial manner? Non-trivial means at least one of these spots, one of these scalars is non-zero, at least one is non-zero. How about I put 1 here? Can you find some other scalars? Because if you can, then that's it, right? This is giving me a non-zero combination. I already put non-zero there. So can you complete this? Can you find other scalars? Yeah, 1, 1, -1, correct. And you see, honestly, the reason is this guy is already a linear combination of those. Right? Because we already saw that this is a spanning set, right? This already forms a spanning set. So anything is a linear combination of those. So that that doesn't help with linear independence when you're already adding something that is linearly depending on the other two, which means a linear combination. Then you can't hope for a linearly independent set that way. So let's think about an example which is more abstract. P1 is the set of all polynomials of degree at most 1. Polynomials of degree at most 1 will look like this: a0 plus a1x. Well, the coefficients a0 and a1 are real. So these are polynomials. Why didn't I say polynomials of degree 1? And I say at most one in this definition. Because it's not clear that this polynomial has degree 1, unless A1 is non-zero. A1 could be 0. Then if A1 is 0, then this is a polynomial of degree 0. Okay. Polynomials of degree less than or equal to some number, they form a vector space because you can linearly combine them and so on, and you can check that using the axioms. But if you fix the degree at a point, say, I'm just collecting all the polynomials of degree 1. All polynomials of degree 1 is not a subspace because the 0 vector is not there. 0 is just 0 plus 0x, and that is a polynomial of degree 0. So now this is a vector space, right? And inside this vector space, I'm asking if this is linearly independent or not. 2 plus x is one of these vectors, right? 4 minus 5x and 1 minus 3x. So I want to show that this is linearly dependent. And the reason for that is because if you take 2 plus x, you can write it as 1 times 2 plus x. We can write it as, or let's just give you the coefficient. So minus 1 times 4 minus 5x plus 2 times 1 minus 3x gives us the 0 vector. That's an easy check, but you might ask, where did I get those coefficients from, right? I mean, where did I get those? So whenever you have a question like that in linear algebra, you have to write it down and you get a system of equations to solve for it, right? So once again, I'm asking whether I can find non-trivial solutions to this system. That's what I'm trying to answer. Yes, not randomly, because if I put randomly, then the answer will not be 0. Exactly to answer the question, how did I put 1, negative 1, 2? Okay, if you have no idea where the 1, negative 1, 2 came from, this is the way to go. And so let's see what we get. We get a system of equations to answer this, and it's a homogeneous system of equations. See, 2 alpha plus 4 beta plus gamma, right? This is the constant term, and then you have x term. What times x equals 0? Alpha minus 5 beta minus 3 gamma, right? So this is equal to 0. The only way that a polynomial of degree at most 1 equals 0 is the coefficients must be 0, right? So notice that this is for all x's, so it's a polynomial. A polynomial of degree 0 is 0 because the 0 vector means the coefficients are 0. That's right, and it's homogeneous. So what you get is the following system of equations. The augmented matrix has a 0 column on the right side because it's homogeneous, right? And you want to solve this system now. Okay, so you can do the row reduction and try to find all the solutions. Okay. But it, yes, by elimination. But it's clear already that there will be one free column at least. That's the point. I don't want to solve it completely right now because everybody can do it. But it's clear that because it's 3 by 2, once you do the row reduction, is it possible to have all pivot columns? Well, remember that the number of zeros should be increasing, right? Strictly. So what happens is you can't have a case where you have no free columns. At least one of these columns should be free. And that means there are infinitely many solutions already out there. Is that clear? So it's not just the 0, 0, 0 solution, which we were hoping for. For linear independence, only 0, 0, 0, right? But here it's clear. In fact, we can find the solution, right? Should I spend some time and solve the system, or it has infinitely many solutions? Let me at least write that. Infinitely many solutions. By solutions, I mean alpha, beta, gamma, right? Including one of them is, of course, 0. Yeah. So there are non-trivial solutions. Yeah. Yes.
When you do 0, 0, 0 for alpha, beta, gamma, why did we take it's 10 or is it 0?
Here?
We can take any value for gamma because it will be 0, 0.
Yeah, that's right. I mean, we can put any value. So you don't have to limit ourselves to 0. That's the point. That's exactly the same remark as the last one. So this system has infinitely many solutions. That's what I want to say. Once again, you know, if you want to write it in the form of the augmented matrix, it should be 1, 0, 0, 1 because of the 1, 0, 0, right? And 0, 0, right? So this is the free column, isn't it? That's what I'm saying. So it means infinitely many solutions.
So in general, if we have the 3 equations with 2 equations with 3 unknowns, we have infinitely many solutions.
In general, if we have 3 equations in 2 unknowns,
No, 2 equations with 3 unknowns.
2 equations in 3 unknowns.
We have infinitely many solutions.
Not necessarily, because let's think about it in what it means in R3, right? R3, this means you're thinking about 2 planes, right? These 2 planes can be parallel, but if the system is homogeneous, you know that these planes have to pass through the origin, so they will intersect. Once they intersect, at least there is a line of intersection, or they are the same. Either way, you will have infinitely many solutions once there is one common point, which in this case would be the origin. That's the meaning of homogeneous, by the way, right? You're enforcing that plane to pass through the origin. Once the 2 planes pass through the same point, then they generate infinitely many intersection points.
Does it need to be homogeneous?
If it's homogeneous, what you're saying is absolutely correct. Yes. And that's the point here. Yes. Very good question. Okay, so linear independence, right? So what about 2 vectors? So we have 2 vectors inside any vector space. So S is this, is linearly independent. Do you think, so this is a rather simple example. If I have 2 vectors, if I give you 2 vectors rather than 3, how can you tell whether they are linearly independent or not. So linearly independent means any linear combination of these two, which leads to 0, then the coefficients must be 0, right? So when would they be otherwise linearly dependent? So some non-zero selections, so linearly S is linearly dependent when we can find alpha 1 and alpha 2, right? At least one of them non-zero, right? Such that, let's call it beta, right? Isn't it beta? Alpha beta, such that alpha u plus beta v equals 0, right? So at least one of them is non-zero. Say beta is non-zero. If beta is non-zero, then can I write v in terms of alpha? So v is a scalar multiple of u, or the other way around, right? I mean, or u is a scalar multiple of u. So that's the only way you can get linearly dependent sets with two vectors in it. So it's very easy to determine, right? So whether a set with two vectors only is linearly independent or not. If one of them is a scalar multiple of the other one, then it's linearly dependent. If not, then, right? So there is a notation for this situation. U parallel to V. It's a notation. If UV is linearly independent. Right? And think about it, linearly dependent, sorry. So when a vector, when one of them is a scalar multiple of the other one, and think about it geometrically, right? So a scalar multiple, positive or negative, it means these vectors are parallel if we are in R2 or Rn, right? So that's notation comes from the usual. So in P1, do you think 1 minus x and 5 minus 5x are parallel? What do you think? Right. These are parallel because one is a scalar multiple of the other one, but 1 minus x is not parallel to 5 minus 4x. Right? So together, they're linearly independent. Right? So any questions so far? Some remarks. A subset of a linearly independent set. So the question I have in mind is, if you have a set that is linearly, set of vectors, right? That is linearly independent. Then how we could possibly come up with some other examples of linearly independent sets. If you make it smaller, like by removing some vectors, they remain still linearly independent of each other, right? It's clear. So a subset of the linearly independent set is linearly independent, right? Now, if they were already linearly dependent, then which operation about sets will still have them linearly dependent? So if I remove some vectors, who knows, maybe then they lose the dependence. But if I add vectors to it, they're still linearly dependent because a bunch of them already are linearly depending to each other. So this logically makes sense, right? So adding elements to a set gives you a set that is larger, right? So it's called a superset. So superset is sort of the opposite of subset. So a super set of a linearly dependent set is linearly dependent. So let me just underline the independent here versus dependent, okay? So in R3 example, is this set linearly independent? X equals 1, 2, 3, Y equals 0, 3, 2, Z equals -1, 1, -1. Is this set linearly independent? How do I answer this question? Obviously, this is in R3, isn't it? So I have a set of 3 vectors in R3, and I'm asking you, do you think this is a linearly independent set or not? So how do I determine that? So we don't know, right? I mean, we just by just staring, sometimes it's hard, right? So what we do is we just set up alpha x plus beta y plus gamma z equals 0, which is 0, 0. So that means what exactly? So remember, by the way, a couple lectures back, when I talked about linear combinations of column vectors, I said you can immediately view this as a matrix multiplied by the coefficients, which is exactly what we've been doing here too. Whenever I form a system, I did that, you see. To what I'm saying is I put 1, 2, 3 as a column, see, and then 0, 3, 2, right? And then -1, 1, -1 multiplied by alpha, beta, gamma equals 0, 0. This is the same thing as what I wrote above. Do you agree? I mean, this is the point of view that you should always have in mind, by the way, you know, whenever you have alpha times 1, 2, 3, right? Plus beta, you view it as column vectors, right? Another way of writing it is you put alpha, beta, gamma, the coefficients as the column vector as an unknown multiplied by a square matrix whose columns are, what are the columns? X, Y, Z vectors as the columns. If you're in doubt, look, if I multiply this by alpha and this by beta and this by gamma and add, right? What do I get on the first spot? Alpha plus 0 beta plus -1 times gamma should be 0. This is exactly this row by this column, isn't it? You see 1, 0, -1. Only the first coefficients will contribute to the first equation, which is 0. So now I'm asking this, you see this problem, the problem boils down to solving a system. And now I want to look at it from another equivalent point of view, matrix multiplication. I could have done using the augmented matrix as well, but I did it this way now. So if I do it this way, how can you determine whether the system has a unique solution or not? Correct. That's a very good point. But what if we just fail to find something like that, and still it might, you know, there might be other cases, right? So so yeah, one way is of course to form the augmented matrix, and it's homogeneous, so we have 0 on the other side. Is there another way of looking at that problem and see if there is a unique solution or not? Especially that this is now a homogeneous system. Algebraically, you can find the determinant of this matrix. Right? It's not hard to find the determinant using the cofactor expansion, for instance. Along, I would say, the first column, what would be the determinant? Positive, negative, positive. So 3, 1, 2, negative 1. And then the 0 goes away, plus negative 1 times 2, 3, 3, 2. Right? What's the determinant of this matrix? Minus 3, so minus 5, minus 4, minus 9, I think, right? Did I do it right? So minus 5 minus negative 5, I think is 10, right? Is it what I did? Oh no, it's indeed 0, right? So what does that imply now that the determinant is 0? So if the determinant was non-zero, right, then there would have been a unique solution, which is the inverse of this matrix by 0, which is 0, right? But there is no, this matrix is not invertible. And that is the way to say that this square matrix has some sort of linear dependency, as he was suggesting, that maybe one vector, one row is a linear combination of the other. So instead of searching for these relationships, find the determinant, and determinant will determine that for us. Okay, so determinant is 0, so that tells us that there is some linear relationship. In fact, to discover that relationship is a different story. What I would do is I perform Gauss elimination, right? So if I do that, so I just report the final results. But I have an important question to you. Just make sure that you're following exactly this. So this is in fact, I even wrote for you here the Gauss, the reduced row echelon form. Okay. Okay. So Gauss Jordan even. But you don't have to do that. So, but staring at this reduced row echelon form, do we have any free columns? Is one thing that I can ask, right? Do we have any free columns? No free columns. No. These are the pivot entries, and this is the free column. That's the free column, right? So that means infinitely many solutions for alpha, beta, gamma, right? Okay. Also, the last row is 0, right? That means that matrix, by the way, is not invertible. Remember the criterion for invertibility, right? When you find an echelon form, you have to see the 0 rows in the end, in the bottom. Okay, so, but can you find that sort of linear dependence that some linear combination, non-trivial linear combination of x, y, z will give us the 0 vector according to the reduced row echelon form that I found here? Can you tell me what is that relationship? So this is the x column, and this is the y, and this is the z, right? Those vectors, right? X, Y, Z. So it's hard to say what sort of relationship these have with respect to each other and between each other. But after you perform elimination, you end up getting some simpler vectors. And particularly, these are the standard, vectors, right? Okay. So do you see, can you write this as a linear combination of those? This one, which is the free column. Can you write it as a linear combination of those two? Isn't it -1 times this, +1 times this? That linear dependency is preserved and it's not changed in the process of row reduction, because in the row reduction, imagine, for example, one column is a multiple of another column. When you do the row reduction, the relation between columns does not change. It remains the same, because all you're doing is, so if this column is 2 times this column and you do the row reduction, this column remains 2 times this column throughout all the process. Okay, and this is a very important fact. It's easy to follow, but it's extremely important. And that's the clue to saying, oh, then I'm saying, I'm discovering that z equals x minus y, or minus x plus y. Look, minus this plus that. In other words, z is y minus x, isn't it? 0 minus 1, 3 minus 2, 2 minus 3. Oh, by the way, this is -1. I wrote it incorrectly, right? Z is minus 1. Okay, so we also learned something here, that if you write a bunch of column vectors and you wonder if one of them is a linear combination of the others or they remain linearly independent or not, what you can do is you can do the row elimination process, and in the end it's easier to find the linear relationship between the columns, because the echelon form is able to give you that, to uncover that sort of linear relationship much more easily. So that's something that's very helpful. So they are linearly dependent. Okay, so can I come up with the linearly independent subset of these vectors, for example? So I know that z is y minus x. This is what I just realized. Z is y minus x, right? If I just drop the z, would the set be linearly independent? This too. You can just approach the problem exactly similar to what I did here, but the coefficients will be in R2. I mean, the solutions will be in R2 because you're just talking about two vectors now. So if you put alpha and beta, it's going to be two vectors. So it's going to be a matrix like this, right? So what about? So let's call it S1. S1 equals just X and Y alone. So then you're thinking about alpha X plus beta Y, making it equal to 0, 0, 0. This time you get the augmented matrix X, which is 1, 2, 3, right? So it's like dropping one column, right? 0, 3, 2. And you don't have that third column, but you have augmented the 0. So if I just do the reduced row echelon form, what do I get? Well, what do you think? I just dropped one of the columns, the third columns. What would be the reduced row echelon form of this? Do I have to sit down and calculate it now that you have the reduced row echelon form of the three columns all together? It will be the same because that was the third column, right? So anything that I've done before will work still. It's 1, 0, 0, 1, 0, 0, right? So it's like removing this, right? And 0, 0. This would be the reduced row echelon form. And so what do you think? What are the solutions of this system? No free column, right? So X is 0, Y is 0. That's it. Or alpha. I call them alpha and beta. Alpha is 0. Beta equals 0. So these are linearly independent, but even more conveniently, I would say, because these are two vectors. I'm just wondering about their independence. Is one of them, are these parallel or not is the question. Obviously, they're not parallel, right? I mean, one is not a multiple of the other one. So it's clear that these two are linearly independent. So yeah, you can think about this in the context of, okay, I'm having a linearly dependent set. Can I just remove some of the vectors so I just get rid of the dependency? Yeah, this is true. You can think about this process and try to eliminate some of them. So you come up with a linearly independent subset. This is possible in general. Well, at the price of maybe you just drop everything out and you just get one of them because all others were multiple of this one, right? You have to drop one by one to minimize it to just one vector. Yeah, that's also possible. Now it's time to think about the basis, okay? So now that we have both of these, what are both of these? I first define spanning sets, also define linearly independence. It's time to find a basis. So a basis for a vector space, is a linearly independent spanning subset. So this is like an sort of an optimization problem. When you search for a basis, it's like an optimization problem. First of all, whether any vector space given to us has a basis or not, should have a basis or not, is a very deep question. The answer is yes. But to prove that, you need some axioms from set theory. For example, one of the axioms in set theory is called axiom of choice. Equivalently, you need what is called Zorn's lemma. So whether any vector space has a basis or not, right? This is somehow too much to ask, right? You're looking for, it's like I have a list of properties. Can you find a set with that property? What are those properties? You want it to be linearly independent. You want it to be spanning at the same time. So the two required properties are all somehow going against each other. You know, in some sense, this is the right balance between two properties. So spanning property So the spanning property makes a basis somehow too large, right? Right, because to be a spanning set for a vector space, it means you should have enough vectors in it, right? So you would not run out of any vectors when you generate all the linear combinations. So when you're searching for a spanning set, you're more worried about having enough vectors in it or not, right? Than anything else. But the linear independence somehow goes against that, you know. When you're thinking about finding linearly independent sets, you're just constantly worried about, oh, if I add one more vector, you know, do I still have linear independence between them or not? So you're constantly thinking about not making it larger and larger, you know, because you will lose linear independence. So linear independence property makes a basis somehow too small. So, and it's amazing that these two sort of, in some sense, optimal optimization problem will have always a solution, that you can find a set that is not too big, it's not too small from this point of view. It's right about the correct size, okay? That you have both linear independence and spanning. So you have, and of course for R2 we have an example like the standard basis as that property. We showed that it is spanning and it's linearly independent as well. So yeah, there are basis, you know, for R2. And in fact, for any vector space, there must exist a basis. Okay, so here is an example. The set 1 plus x, 2 minus x is a basis for this polynomial space P1. Remember, P1 was the set of all polynomials of degree at most 1. So it has all the constant polynomials, all the linear polynomials. So this set is a basis. What should I check? I should check two things at the same time, right? So one, B is spanning. How do I check that? Similar to the examples we saw. I'm asking whether any linear polynomial like this can be written as alpha times 1 plus x plus beta times 2 minus x. So I'm asking, can I find alpha and beta, right? So this is any, right? For any given A and B, can I find alpha and beta, right? That's the spanning question, whether this is a spanning set for P1. Does that lead to a system of equations in alpha and beta? So yeah, what is the what's the system, right? So 1, 1, 2, -1. And notice how I found them. Look at 1 plus x, right? I put it as 1 plus x. So this is like the second spot. And 2 minus x, 2 minus 1 times the second one. So, and I'm asking myself whether this system has a unique solution. I mean, has a solution or not unique, just has a solution or not. Well, what is the determinant of this? Is non-zero, so this matrix is invertible. So if I call this A, then alpha beta should be A inverse times AB. In other words, I just answered the question by looking at the determinant of this matrix, 1, 1, 2, -1. Or I could have done reduced row, I could have done Gaussian elimination and so on and so forth. So this means that B is spanning, right? Now I have to address one more thing. And what is it? B is linearly independent as well. But notice that something interesting happens. I'm kind of working as a sub-problem of this one because the linear independence means you can write 0 as alpha times 1 plus x plus beta times 2 minus x. And you're wondering whether alpha beta must be 0 only. But that's a sub-problem sort of, right? I mean, 1, 2, 1, -1 again times alpha beta, but the right side is 0 now. So does this system have a unique solution, alpha equal beta equals 0? Exactly, because this is the determinant is non-zero. This means alpha equals beta equals 0, right? Because again, you find the inverse of that matrix, multiply by 0, 0, you get the 0 column. You come up with a nice criterion in some sense then. If I have, yeah, if you have, for example, in the polynomials with degree 1 at most, if you just put these things in a column, right? Like what do I put it in a column? So you see 1 plus x. So I put it as 1 plus 1x, right? And then 2 minus x, 2 minus 1x, right? So this becomes just a numerical matrix, no x's in it, right? If the determinant of this square matrix is non-zero, then the set is not only spanning, it's also linearly independent. So that's a nice criterion for showing that something is a basis. But please note that I pick 2 vectors and the coordinates have 2 also. So it's a 2 by 2 matrix. So determinant makes sense. So later I will put this in a more official form by defining what is called the coordinates of a vector. So like 1 plus x in the so-called standard basis of the polynomial spaces is denoted by 1 plus 1, like 1, 1. And then, so this is the coordinates of the 1 plus x vector. And this is going to be the coordinate of 2 minus x. So this gives us a numerical matrix. So we can check the determinant of that to see if you're working with a basis or not. But yeah, as I said, many questions in linear algebra would naturally boil down to a system of equations, to answer, do you have any solutions? How many, if so, and so on. So any questions? Okay, yeah, you can still ask questions, but I think this is it for part 1, right? Fall semester.